Hello. I'd like to continue my discussion on quaternion. So last time we just introduced a quaternion that is basically a four-dimensional vector you can think of, but it's more like also you can think of like an extension of like complex number that have like four complex components, four different types of complex components. So this ijk, like all of them, if I square that, will be equal to -1, and at the same time, like when I have cross product between them, they kind of operate kind of like cross product in 3D space of different assets in 3D space. I have I times j is equal to k, j times k equal to I, and k times I equal to j. And if I multiply in the other direction, I will have like minus, have a minus of that thing instead. So it does not commute basically, the multiplication. And we mentioned that if we consider any point on the unit ball in the four-dimensional ball, such that like a squared plus b squared plus c squared plus d squared is equal to 1. And for any points on this four-dimensional sphere, and I can have this stereographic projection. So, and each point on this sphere will project to some point on the imaginary plane. It's basically the imaginary plane now is will be a three-dimensional space because I have like three different dimensions for the imaginary axis. Basically three different imaginary axes here, and basically the mapping will be something like if I have A, B, C, D, the quaternion will map to like A over B over A plus 1 and C over A plus 1 and D over A plus 1. This is in 3D. This 3D. This is a quaternion. So now, and we can go and also the opposite direction from this three-dimensional base space. So it'll be like maybe I write x, y, z here, and map it back into a unit quaternion. So such that like my A, B, C, D will be like 1 over s, 1 minus s, and x, y, and z. So where s is equal to 1 plus r squared over 2. So that's a quick review of what we did last time. And then what I like to show this time is that probably the one of the most widely used application of quaternion is that if we think of like okay, let me write first of all, maybe I write a quaternion in this form. So basically, if I have a unit quaternion, I can write it like this. I can write as a, maybe I write like this, C plus S U. So where U here is is basically you can think of like a three-dimensional vector, like each of the axes defined by the ijk here. So it can be like, for example, A, maybe I should use A again, alpha I plus beta j plus gamma k, let's say. And this U is a unit vector, so it's normalized. So I have alpha squared plus beta squared plus gamma squared is equal to 1. And also this is a unit vector, so therefore like CMS is kind of normalized as well. So therefore I have C squared plus S squared is equal to 1. Actually, you can very easy to verify that. Actually, I can verify it now. So because if I, by the way, if I have a form something like that, the inverse of this guy is actually is equal to C minus SU, because if I have like C plus SU multiplied by C minus SU, So I have like c times c here, and minus c times su here, plus s times cu here. These two will go cancel, and then minus s square u times u. Now when u times u, what do we get? Like for the u times u here, I will have like this alpha, beta, gamma, I, j, k. Okay, maybe I write u again is like alpha I, k plus beta, j plus gamma, k. So when I multiply u times u here, multiply alpha I plus beta, j plus gamma, k. So I have some cost term, and also like cost term I mean like I times j, j times k, and k times I. And also some terms like multiplying itself. When I multiply by itself, I have like minus alpha square, minus beta square, minus gamma square. Right? That's only give me minus the inner product between u. If you think of u is like a vector with just alpha, beta, gamma. And also for the cost term here, last time as we show like this is actually will just give us like the it's actually just equal to the cross product, vector cross product. So therefore it's like actually u cos u in that case. And of course these two are same vector, so u cos u will be just equal to 0. So therefore this is actually gone, so I only have minus u dot u here. So therefore I have this guy here is actually equal to c squared plus s squared here. So therefore it's equal to 1. If this is also normalized somehow. So anyway, like I have a quaternion can be written in this form. Therefore, like a unit quaternion can be of course like for arbitrary quaternion I can write like this. Only when it's a unit quaternion, I will have like c and s here is a normalized such that c squared plus s squared is equal to 1. So let's see. And why I like to write like this? Why I write c and s? Actually, I can, instead of putting c and s here, let me put cosine phi over 2 plus sine phi over 2 u here. And let me call this q here. So basically what we want to show is that like for any p, any quaternion point, like any point p, okay, p is also a quaternion, so I represent all like for all any three-dimensional points, if I represent as a quaternion, that will be some a plus bi plus cj plus dk, right? And this p times q inverse, again q inverse is just equal to cosine phi over 2 minus sine phi over 2 u here. We will show that this is actually just equal to rotating p. So basically my p here, if I consider in a three-dimensional space, let's say I have, maybe I draw here, maybe even use a different color. So let's say I have some point p here, this is some point p here, and let's consider u is somewhere here. This is u here, u hat here. So this operation, if I define a q like as like cosine phi over 2 plus sine phi over 2 multiplied by u hat here, this operation here will be equal to rotating this p along this u hat with phi degree in the anti-clockwise direction. Okay, let me rewrite this p as something like alpha. Okay, let's go back to black here. P equal to alpha plus beta p, something like that. P, maybe I will write p hat. So p is a vector, so it's something like p hat is equal to some a pi I plus b pi j plus c pi k, let's say. And I can also decompose this p hat as like, let's say, au plus bu perpendicular, let's say. So what I mean here is like I can decompose this p, okay, p hat here by two direction here. So this is something like I have this p here, p hat is this direction, maybe I use different color again. So this is a p hat this direction. I kind of assume p hat is kind of normalized, and then I can write it as like some with these two components here, right? One is like along this u hat component, the other one is like perpendicular to this u hat component. So maybe I can zoom in here, something like this is p hat here. I have like this is like u hat here is something like p hat is equal to au, or maybe I skip the hat here, au plus bu perpendicular, so along this direction. So so therefore like I will basically rewrite this something like this as like au plus bu perpendicular. This is my p now. This is my p, and know that like if we go back, this like is the graphic projection, like from quaternion to 3D and the other way around. The direction of the vector in the 3D space only controlled by the imaginary components, right? As you can see here, in 3D space, after the conversion is just b, c, d over by a plus 1. All of them scaled by the same factor, 1 over a plus 1. So therefore the direction is only affected by this imaginary part here. So therefore like this actually, when I expand this guy here, this of course alpha beta is real, and this part specify the direction completely. And then I further decompose this guy again. So originally I said this is equal to p hat, some direction p hat. Then further decompose into au hat, au plus like bu perpendicular. Okay, I skip the hat here every once in a while because it will be understood that u is equal to u hat. So the vector here is I kind of normalized, like u and u hat, u perpendicular, both of them I'm kind of normalized. And I can also consider like let's see, u cos, let me consider maybe another color again. UO is this direction, UO. So UO is equal to U perpendicular, U cos U perpendicular. So note that I have a right hand rule here. If I draw a hand here, so you see this is the finger, this is the thumb here. I have the right hand rule. If I cross like first pointing up, my finger pointing up here along this U hat direction. If I curl back like to the direction of like U perpendicular here, I'm pointing to the direction of the vector. So if I have U hat or like U cross like U perpendicular, I guess U naught is this direction. If I have a left hand rule, it will be the other way around, we're pointing in this direction here. But the convention like for cross product is the right hand rule. So I have the U naught is like this direction. So basically U naught is perpendicular to U and also U perpendicular. Then like what will be rotating P 5 degree would be like. That would be basically, if you look at the P voltage, basically my P voltage, what do I expect? This real component doesn't change because it doesn't change to that when I rotation. This alpha and beta here only affect the scale or the length of that vector, so it doesn't affect the orientation. So alpha and beta will be the same, but now the direction here, u will be the same as well as AU here, but my u perpendicular will basically, if I look down, I have an eye look down in this direction looking down, so basically I will have, this is the original u perpendicular here. So after rotation, this rotation is 5 degree, so my u hat here is a pointing upward, so I cannot draw it, it's just a straight vector pointing out of the screen here. So if I rotate by 5 degree here, so my new vector, this position here, would be basically u hat, this, let me draw it better. So if I rotate 5 degree here, it's somewhere here. So this vector is equal to u perpendicular times cosine phi, so it's scaled by cosine phi. That's the vector here is equal to this vector. At this vector is basically this direction here is u naught. So if you use, again, like if my eye is looking downward here, like u hat, or the u is directly pointing out of the screen here, and I have u perpendicular pointing in this direction, like just to the left, and then u naught is pointing in this direction here. So therefore this vector, this rotated vector, is equal to u perpendicular times cosine phi plus u naught times sine phi, something like that. So therefore, like my rotated vector, what I expect maybe I use this, the changed part is like times b times u perpendicular cosine phi plus u naught sine phi. So this is rotated by 5 dB, by 5 degree counterclockwise. Along u naught. So okay, that's what we want to show basically. This is the starting P here. I want to show that if I multiply by Q and multiply by Q okay, I think this is wrong. Actually, I should be like that. Multiply by Q on the left hand side and multiply by Q inverse on the right hand side. The antifact will be rotating by along u naught by 5 degree, and so therefore I expect like this will be equal to P rotate, equal to this guy here. So that's why I am now next I'm going to show that. Let's see. So I guess I'll erase most of the stuff here. And I think I may have enough space here. Let's see. So again, I have my P here is here, right? P is here. My Q is here. Q is here, right? Q inverse is equal to this guy. Q inverse is equal to this guy here. And note that if I write quaternion in this form, like let's say Q1 is equal to A plus BU, let's say, and Q2 is equal to C plus DV, let's say. And we have did it a couple times now. I have Q1 times Q2 will be equal to A times C, so this times this, and then this time this one will be plus ADV, and then this time this one will get BCU. So it looks like this is vectors here. And then this times this one here, I will have, oops, so this is like very annoying, equal to B times C. Oh, I'm sorry, actually, I think I cannot see here clearly here. So this one is AC here. So will be, okay, this time this guy will B times D. Then I have U cos V, but also have like minus B times D, the dot product here, U inner product of U and V. So this is a kind of equation that is like pretty easy to show, and at the same time it's very handy to use. So now then let's see, I want to compute this way. I want to compute this. I want to show this is actually equal to this guy here. So I'll just do like Q times P first. Q times P is, maybe I just call this C and S like for convenience. So I have like C plus S times U. So I guess I will skip the hat here. C times S, C plus S times U. Again, U, this is vector, be very careful. I will skip this under bar to will be understand like U, U naught and also U perpendicular are vectors. The rest is a scalar. And my P here is a alpha plus beta times AU plus BU perpendicular, right? So it's just like that. So now I can use this equation here. Let's see, if I expand that, I have like C alpha and then plus say C beta A plus AU plus BU perpendicular, and I have one more term here like let's see, have this multiplied by this is like plus S alpha U, and then this multiplied together I have S beta plus S beta U cos this guy, U cos AU plus BU perpendicular, right? And then I have minus S beta, the inner product, UM AU plus BU perpendicular. So then let's see, I just copy some of this as C alpha plus C. Let's see, I have C beta, maybe I just copy it here, AU plus BU perpendicular is the same as alpha U, and then S beta. So U cos this AU now I can remove some terms. U cos U is just equal to 0. U cos U perpendicular, you see what's that? U cos U perpendicular is just equal to U naught, right? So therefore like I have S beta BU naught. BU naught. And then for this guy I have what? I have U and U perpendicular kind of perpendicular to each other, so this the next term is equal to 0, but I have like minus S beta A basically. So U are normalized, so S beta A here. Let's see, anything I can actually so maybe I just group the terms and then I continue. So basically this is equal to C alpha minus S beta A. This is the real term, and then I have was C beta A plus S alpha. That's the coefficient for U. And then I have U perpendicular. Basically, we're going to C beta B U perpendicular, and then I have S beta B U naught. This term here. I think that's it. So this is like Q times P. So this part. So if I want Q times P times Q inverse, then I have this guy here. The whole thing I'm not going to copy the whole thing. It's going to multiply by C minus SU. So C minus SU is equal multiply to this, and then let's see. I have real terms here, C alpha minus S beta A. This multiplied by C, and then let's see. Maybe I will expand it anyway. So this is multiplied by C. So C squared alpha minus CS beta A. So this multiplied by this term here. That take care of the real term. Then I have, let's see, SU multiplied by this guy here. So minus S. Okay, again, I will just expand directly. Well, it's okay. I'm not going to expand that. XC alpha minus S beta A U. Okay. And then okay, and then C multiplied by the rest of this term. So I have like plus C beta. Okay, that's so C beta A plus S alpha U plus C square beta B U perpendicular plus, okay, my handwriting is too bad. This is S, I think. CS beta B U naught. Okay, so that take care of the real terms multiplied by all the terms, I think, like C multiplied by all of these guys, and also this guy multiplied by, okay, this guy multiplied by C, but this guy multiplied by SU. Did I do that already? I forgot. Oh, I did that. This guy multiplied by SU. Yeah, I have that also. So, okay, I think I take care of all the real multiplied by something else. So now only the cos terms. So U multiplied by this guy. So I have minus SU multiplied by this guy. So I have basically lots of inner product. I have S. The inner product, the order does not matter, but anyway. So I have minus here. I should have plus here for the inner product. So I have S plus S C beta A. Maybe I just write like that. Alpha U plus C beta B U perpendicular plus S beta B U naught, and the whole thing inner product with U. Yes. So that take care of like partial, not finished actually. That's only for this term here. So I also have the cross product term. So it will be like this guy cross with this. So I have a minus sign here as S C B A. Maybe I didn't copy the whole thing. S alpha U plus C beta B U perpendicular plus S beta b u naught, the whole thing cross with u. So I don't have a angle bracket here, so I just have curly bracket. So I should be able to cancel lots of stuff, but let's see. So first of all, like this is inner product, like for this guy here, so inner product will be just because u perpendicular and u naught, both of them perpendicular to u, so this will be all gone. And then for the cross term, for the cross product here, like cross product with u will be gone, so this term will be gone here, and u perpendicular cross with u, so will be, if I go for right hand rule here, I have my hand here, so see my finger pointing this direction, so I can, yeah, this is not the right hand, this will be the left hand, so right hand will be something like I trying to do u perpendicular, so my finger like pointing this direction. Now I curl towards my u here, so therefore my thumb is like pointing this direction, so it's like, therefore it's like minus u naught, so this is minus u naught, u perpendicular cross u is minus u naught, and u naught cross u is u perpendicular, basically this is u perpendicular, so u perpendicular and minus u naught. So let's see, now then I guess we can start, maybe I erase some more here. So this is, so for this guy here, u times u is just equal to 1. So therefore here I have SC beta A, so this is CS beta A, I can cancel one of these terms here. And I have like S square alpha here, and I have C square alpha here. This group together actually will give me alpha, right? Because C square plus S square is equal to 1. So Q is a normalized quaternion, so basically. And or you can think of C is just equal to cosine phi square over cosine phi over 2, and S equal to sine phi over 2. So cosine square phi over 2 plus sine square phi over 2 is equal to 1. Okay, and let's see what else I can simplify. So I already take care of this term, right? And then so this whole thing is like done actually, kind of. And then like u naught here, I have u naught here, so I have u naught here is S Z beta B u naught. Okay, this exactly cancel, this is very happy. Okay. This got cancelled. And this one I left is a minus S square beta B u naught, u perpendicular. So this can go with this guy here, and let's see what else. And for this guy, let me check. I have SC alpha. I have SC alpha. There's a minus sign here. CS alpha u and SC alpha u. Again, this can get cancelled. And this guy here, I have plus S square beta A u. This is a C square beta A u. So this can group together to get me beta A u here. So this is sine square beta A u plus cosine square beta A u. So it's like, so okay. Finally, I should have something like, so therefore I have alpha here. I have plus beta A u here, right? That's beta u here, and then I have this u perpendicular here. Go with this guy is beta bc square minus psi square u perpendicular. I think like more or less that's all the term is that. Let's see. I think so. I already see like this pretty similar to this guy now. So therefore it's equal to alpha times beta, like beta I can group together. That's AU here. I get this term already now. Plus B, and then I have a U naught term is missing. Actually, U naught. Oh, okay. This should not be cancelled. So because like here this should not be cancelled. This is plus U naught here. This is have minus and minus again. This is also plus U naught. So I have CS beta B U naught, and this is also CS beta B U naught. Actually, I have two of them. So I beta put it out. So I have two CSB. B already write it here. CS U naught. And then I have this against U perpendicular. So what I'm saying that here I'm missing like two B beta CS U naught here. Missing this guy here. So this term here like U perpendicular beta I put it out. I have plus B square minus S square U perpendicular. And then of course then you see this is just cosine square phi over 2 minus sine square phi over 2. And if you still remember some of this trigonometry identity, we have cosine phi plus maybe I say alpha plus beta, or like I can think like that, like just remember that like EI, this is this Euler equation, right? EI phi is equal to EI alpha cosine alpha plus I sine alpha, and EI beta equal to cosine beta I sine beta. So if I have EI alpha times EI beta, so this is also equal to the product of these two guys here, but at the same time this is equal to EI alpha plus beta, so therefore it's equal to cosine alpha plus beta plus I sine alpha plus beta. And if I expand this, multiply these two, I will get cosine alpha cosine beta minus sine alpha sine beta plus I cosine alpha sine beta plus cosine alpha sine beta. So this gives me equation like cosine alpha plus beta equal to cosine alpha cosine beta minus sine alpha sine beta, and sine alpha plus beta is equal to cosine alpha sine beta cosine alpha sine beta. So therefore like I have basically erase some of this, give me some space. Cosine square phi over 2 minus sine square phi over 2 is actually just equal to cosine phi. Right, because this is equal to cosine phi over 2 plus cosine plus phi over 2. And you can use this equation here, cosine alpha plus beta, this one is equal to cosine phi over 2 cosine phi over 2 minus sine phi over 2 sine phi over 2. So basically cosine square, therefore it's cosine square phi over 2 minus sine square over phi over 2. So okay, so therefore this is actually cosine phi, and this is 2 cosine phi over 2 sine phi over 2. By similar token, this is actually equal to sine phi, because sine phi is equal to sine phi over 2 plus sine phi over 2 here. And if I use this equation here, it's equal to sine phi over 2 cosine phi over 2 plus sine phi over 2 cosine phi over 2. So therefore it's just equal to 2 sine equal to 2 of them, 2 of this sine phi over 2 times cosine phi over 2. So anyway, so that will finally give us this alpha theta times AU plus plus B cosine, sorry, this should be sine. Sine phi U naught plus cosine phi U perpendicular. And as we said earlier, this is exactly the rotation for phi degree. And this basically the proof, like for quaternion, this multiplication. Okay, I guess I erased the equation. The equation is like something like Q times P times Q inverse, and these are in the quaternion form. So if I have any points here, P in the quaternion forms is multiplied by Q, and Q inverse as a sandwich here. Q is just equal to this thing, like cosine phi over 2 plus sine over phi over 2 multiplied by U here is a unit vector that U is like pointing the direction that you want to rotate. Then this will just rotate the P by phi degree. Okay, I will stop here. Thanks.